Most elements are composed of two or more isotopes, which are either stable and therefore remain the same over time, or they are unstable, which means that they are going to have to decompose in a way that will help them reach stability. And the process of that decomposition is what we call radioactive decay. So the spontaneous change of an unstable nucleus to a stable nucleus. The band of stability is a graph that shows the ratio of protons to neutrons and how that relates to stability. So here we're color coding. Okay, the dark red and black dots represent stable combinations of protons to neutrons. So you can see that that's kind of just the center of this chart right here. Okay, if nuclear fusion happens and it produces an atom that is above or below this line, then you can tell by the colors that that affects the stability. So those nuclei are going to, over time, decompose. Some of them take a long time, like 100 years. Some of them go by in a second. Some of them barely last a nanosecond. It just depends on how unstable they are. The first nuclear process that we're going to look at is the concept of alpha decay, which is when the parent nucleus is just too large. So it needs to lose mass in order to become stable. So the parent nucleus will emit a small alpha particle with a mass of 4, 2 protons and 2 neutrons, which is essentially the same as a helium nucleus. That's why you'll see the symbol sometimes written as He. And then it will shrink into a daughter nucleus that is smaller than what it used to be. Now, obviously, 236 isn't that much smaller than 240. Alpha decay is not necessarily a one-and-done process. A nucleus can emit several alpha particles before it's finally finished and stable. The nuclear equation representations are very similar to what we looked at when we talked about nuclear fusion and nuclear fission. So the concept of parent nucleus being on the left side and the daughter nuclei being on the right side is still the same, and the arrow still acts like an equal sign. When we're looking at these equations, what we'll see is there is always a conservation of mass and a total number of protons. So for example, lawrencium here weighed 256 before it started. On the other side, it shrank down to something that weighs 252, but that missing 4 comes from the helium. So the overall mass has remained 256. There were originally 103 protons, MD has 101. Those missing 2 are now here in the helium nucleus. And as you can see, this alpha decay process can happen to basically any nucleus that is really large. Let's see, things to point out. One thing that I would like to point out is sometimes it won't be written as helium. Okay, there is another symbol for alpha, which is that kind of large lowercase a, and it'll have the same 4-2 symbol, but you just have to recognize that either of these symbols mean the same thing. They both represent alpha decay. It also doesn't matter what order the daughter nuclei are written in. So francium can be written before the alpha particle, or the alpha particle can be written before AT. It doesn't matter because addition rules from math tell you that it doesn't matter what order they're written in. The second process that we're going to look at solves a different problem. So beta decay is when it happens when there's too many neutrons. So we need the ratio of protons to neutrons to improve. So a neutron will turn into a proton. If you imagine that a neutron, so we know they're neutral, okay, neutral happens when positives and negatives cancel out. So if you kind of imagine that a neutron is like a positive and a negative stuck together, if we take this negative and we lose it, okay, all the mass stays behind, but now that negative is going off into its own world. It's an electron and it's leaving. So we're left with the same mass that we had before, but now we have this overall positive charge, which is what a proton is. Okay, this particle that goes flying off has no mass and a negative charge, which is basically the same thing as an electron. So what's happening in our example here, the carbon-14, okay, has an unstable ratio. There's 8 neutrons, but only 6 protons. So what's going to happen is one of those neutrons is going to release a negative charge, and the mass is going to stay the same, but it's going to turn into a positively charged particle, which is a proton. So we're going to keep our mass consistent as 14, but now one of those 14 particles has turned into a proton. So now we have 7 neutrons and 7 protons instead of 8 and 6. And so this has now turned into a nitrogen atom because the atomic number 7 is nitrogen. Okay, that lost negative charge is going to be the electron that is emitted. So there's two different ways that we can symbolize a beta particle. We can either use an E for electron, because that's essentially what it is, or, okay, you'll see the symbol of a beta. So it can either be the B or the -1. It doesn't matter. So here's two examples. Okay, this and this are interchangeable. And again, with nuclear equations, we're kind of keeping mass consistent on both sides of the equation. And then we need the atomic numbers to add up to be the same. So 131 is 131 plus 0. That stays the same. What's different is we have to think about the fact that we need the overall positive charge to be 53. So if we know that one of these neutrons from here is turning into a proton, okay, then we need to compensate for that increase in positive charge by pointing out the fact that a negative charge still exists. It's just no longer a part of the nucleus. And the third type of radiation that we specifically want to talk about is gamma radiation. So this is totally different from the other two because gamma radiation is not a particle. Gamma radiation is intense energy that is released during the other two changes. So if you look at this cobalt-60 atom here, what's really happening to it is beta decay, and it's turning into a nickel. But part of that process, anytime you change the nucleus of an atom, you are going to emit intense energy. And gamma radiation is sort of the thing that we associate with all of those negative side effects to radioactivity. So, causing mutation in DNA and therefore developing cancer or burning skin or, destroying the fertility of soil and nothing can grow there anymore. Okay, all of that is a result of that intense energy that's being lost by the nucleus. The symbol for gamma radiation is 00 because there's no mass and no charge, and then we use the Greek letter Y for gamma. So what you'll see when you're looking at an equation is there will have to be numbers because, we still have mass and we still have protons or whatever. But the gamma particles don't really have anything to do with that. So usually gamma radiation is added as an afterthought to something else that's already happening. So our cobalt here is losing a neutron, turning it into a proton so that it can become nickel, and then that negative charge is being given off. And this change in the nucleus is emitting the gamma energy. So before we talk about the last two processes, I just kind of want to pause and discuss really like the important differences between alpha, beta, and gamma that you're expected to understand. And the first of which is their penetrating power. So if, for example, like if there was a radioactive substance on the other side of the room, what would you really have to be worried about while you sat there and stared at it? The gamma radiation is, of course, just pure energy. So you can see by this diagram, the gamma radiation is going to pass through any small barriers that you give it, and depending on the thickness of steel or lead, it could even go through that. So this is the stuff that we have to protect ourselves from. This is why people have bomb shelters that are made out of super duper thick concrete. It's all in an effort of protecting against that gamma radiation. Slightly more penetrating than that is the beta particle. So even though electrons are really, really small, we have discussed before that they do not have a mass of 0. Okay, they are particles. So they can get through something thin. Okay, but eventually, if you have a thick enough barrier, okay, they will get stopped because they are pieces of matter. And then the alpha particle, even more so. Alpha particles are infinitely larger than beta particles. So much more massive because they're made of protons and neutrons. So you can see by this diagram that the paper could protect you from having alpha particles bombard your skin. Now, of course, it all changes if you accidentally ingest a radioactive substance, but hopefully you're not messing around with that. The other thing that we want to look at is just an example of almost sort of how we discovered these things. So if we have a radioactive sample in here and you're only giving it a very narrow stream to emit its radioactive particles, okay, charged pieces will react in an electric field. So the way that we sort of have learned how to separate these three parts and collect them and study them is if you allow radioactive parts to be emitted through a magnetic field. Okay, the part that deflects towards the positive charge and away from the negative charge is going to be a negatively charged particle. So beta particles are that 0, -1e. Okay, the negative charge is attracted to this plate and it's repelled by this plate, which is why it deflects upwards. Okay, the truth is the opposite for alpha. Okay, because alpha is a mass of 4 and has 2 protons, this is secretly a positive 2. Okay, since protons are positively charged, so it's going to repel away from the positive charge towards the negative charge. And then you can see the last one here, if I just get rid of all this writing, okay, gamma rays are just pass straight through without being affected because they have no mass and no charge and are therefore unaffected. Positron emission is the opposite of beta emission. So in positron, the issue with the nucleus is that there's too many protons, and you need a proton to turn into a neutron. So if we look at this unstable atom, this is a carbon with a mass of only 11, and we know that carbon needs to have a mass of at least 12 in order to be stable. So in this case, we have 6 protons, but we only have 5 neutrons. So basically what we need is for a proton to lose its positive charge and become neutral. So all of the mass will stay behind, but the positive charge will go away, and we'll have a neutron where we used to have a proton. So this is going to turn into boron, which only has 5 protons, but the mass number is going to stay the same because that proton turned into a neutron. So the major difference here is the mass has stayed the same. So this missing particle, this positron that's pictured up here, it has no mass. But if we need the overall positive charge in the universe to stay the same, instead of a -1, a positron has a charge of +1. And that is unlike any substance that we've looked at before. Okay, this number setup is not the same as a proton. A proton has mass, and this is suggesting that it has no mass. So we use the same symbol for beta, but this is what we call an antiparticle. So although it appears to have the same identity, it actually has the opposite identity. It is a beta particle with a positive charge, and therefore is a positron instead of an electron. And the way that this appears in the nuclear equations is very similar. Okay, you can see that the E can be used in place of the B, or the B in place of the E. Okay, it's that +1 that identifies this particle as a positron rather than as a beta particle. But the rules for math stay the same. Okay, 232 equals 0 plus 232, 90 equals 1 plus 89. So we're keeping consistent with our nuclear equations across the board. The last reaction that we're going to look at is called electron capture. And this is almost more of like an accident. An electron that's floating around the neutron, or the nucleus, excuse me, just sometimes gets trapped into the nucleus, and it gets stuck to a proton. So if you take a proton and you accidentally stick a negative on there, now you have ended up with something that has a charge of 0. So you're taking a proton and you're turning it into a neutron. So kind of weird because it's the same elements from before, carbon 11, okay, but this time we're adding a negative instead of losing a positive, if that makes sense. And on the other side, we're going to end up with that 511 boron. So the major difference between this radioactive activity and the other examples is the radioactive particle, the particle that makes the nucleus change, happens before the arrow. So it's adding itself to the parent nucleus and turning into the daughter nucleus. So if we look at another example of this, okay, chromium with a mass of 51, if you add a negative charge to the nucleus, you end up with only 23 electrons, so it turns into vanadium rather than chromium.